Hey, this is Mr. Barr, and I'm going to go over the Math 8 goal number 1, real numbers pretest, version 1.1. All right, so what two integers, let's zoom in a little bit on this. What two integers is the following number between? Do not use a calculator. Square root of 43. Well, I don't know the square root of 43, but I do know the square root of 36. And I know the square root of 49. So I know the square root of 43 is somewhere between 6 and 9. So the technique is find a square root a little bit below the one that's given to you and one above. So the answer is between 6 and, I have 9 right there, which is incorrect. And that is one of the reasons I make these videos before I upload these files to the internet. This should be 6 and 7. There we go. Okay, next one. Fill in the missing parts of the table. So I know that a 0.1 repeating is just 1 over 9. This idea of a single repeating digit, I just put it over 9, and I get the repeating fraction here. Or I get the repeating decimal in fraction form. So 0.1 repeating is 1/9. 0.3 repeating is 3/9, which would reduce or simplify, to 1/3. 0.5 repeating is 5/9. And then, so what is 9 over 9? Well, if I use this rule, 9 over 9 is 0.9 repeating, right? 0.9 repeating is 9 over 9, which is also a 1. I know that. All right. Can the following number be turned into a fraction? Explain your reasoning. 0.235 repeating. My answer is yes, it can be turned into a fraction. Why? Because it's a rational number. Any rational number can be turned into a fraction. It goes on forever and repeats. All rational numbers can be written as fractions. Any rational number can be written as a fraction. I'm not necessarily going to teach you how to do that math, but it can be done. Next one. Since the square root of 81 is 9 and the square root of 100 is 10, what would be a good approximation for the square root of 90? You may not use a calculator. Well, I think it's going to be about halfway between 9 and 10, because 90 is about halfway between 81 and 100. So I'm thinking about 9.5. Since 90 is about halfway between 81 and 100, it should be about there. I'm going to use a calculator to check it. Let's see, what's the square root of 90? Look at that, 9.48. 9.5 is a good estimate. Excuse me. All right, so let's classify each number set based on its most precise. Classify each number based on its most precise number set. A non-repeating, non-terminating decimal is irrational. A fraction is a good example of a rational number. -8 is a good example of an integer. A repeating decimal, well, that's always going to be rational. And a terminating decimal is also always going to be a rational number. Is the following number rational? Explain how you know it's rational. 0.4567. Yes, that's a rational number. How do I know? It's a terminating decimal. It has an end. Terminating decimals are rational. Write the following decimals as fractions. 0.5 repeating, well, I put 5 over 9. 0.8 repeating, 8 over 9. 0.9 repeating, 9 over 9, or 1. This is going to show up on a test. This idea that 0.9 repeating is 9 over 9, which is equivalent to 1. Let's see, the following number is irrational. I'm telling you it's irrational. What makes it irrational? Explain your reasoning. Well, the square root of a non-perfect square is always irrational. If I can't take the square root of it, if it's not a perfect square like 64 or 36 or 100, it's going to be irrational. Now I realize that as those numbers get bigger, you get to things like 400. Well, that's the square root of that is 20. You're going to get to some numbers that you don't know in your head. In that case, you're going to have to take a square root on a calculator to determine that it's not a perfect square. So the square root of a non-perfect square is always irrational. It goes on forever without repeating. So when I take the square root of 10, it's going to go on forever without repeating. Yes, my calculator has to terminate it here because my calculator doesn't go on forever. But this number actually would go on forever. And don't just look at those last two numbers and think, oh, it's going to start repeating. It's doing 6, 6, 6, 6, 6, 6, 6. You can't make that assumption. Well, it's not doing that. It's irrational, so it's not doing 6, 6, 6. Okay. And the final one. Megan made the conjecture below. If a rational number is an integer over 1,000, then the square root of the rational number is rational. So she's saying, if I take the square root of any number greater than 1,000, it's going to be a rational number, which basically means that it's going to, if I take the square root of it, it's going to be a perfect square. For example, the square root of 1,225 is rational, and the square root of 1,600 is rational. So she's picking out two examples and saying, hey, look, it works. See, is it right? So 1,225, square root of 1,225. Oh, look at that. It's a rational number. Square root of 1,600. Oh, look at that. It's a rational number. Oh, everything greater than 1,000 must be a rational number. No. No. Look, the square root of 101, oh, excuse me, of 1,001. That's not rational. Look at that. How about, what's the other one I put? The square root of 1,002. No, that's not rational. So it says, provide two examples of integer numbers over 1,000 that show that Amy's conjecture is false. Look, here are two that Amy's totally, she's not right. She chose two examples where it works. I just chose two that doesn't work. Look, I'm going to choose another one where it doesn't work. Oh, here's another one where it doesn't work. I mean, she gives you two that work. I can give you, well, hundreds, well, technically infinite, but that don't work. Hey, that's the video. Thanks for watching. I'll see you in class. Bye.